Hello, my name is Homero Barreto, and my Panther ID is 6139408.
Hello, my name is Diego Landi. My Panther ID is 6226932, and this is for the class Electronics 2 Laboratory, and this is the experiment 2. So for experiment 2, let me share my screen so you guys can see what's the idea of the experiment 2. So for experiment 2, we were supposed to design a dual buffer input instrumentation amplifier with a 10-volt gain, a bandwidth of 200 radians per second, 0 DC output, and later on we need to test the common mode rejection rate of the op-amp. Ideally, this will be 0, but in reality, it's different. It should be in a range of 50 to 70 dB. So for the first section, we made some calculations based on the ideal behavior of the op-amp. This is the equations that we found, and considering these equations and rearranging all the variables to get like the transfer function, we get these resistors values. After implementing the circuit itself, we changed these values to 1K and 10K, as we're going to see on the next picture. So on this picture, we can see the PSpice implementation that we did. We can see the voltage difference of inputs, 2 volts on the first input and 1 volt on the other input, and the values of the new resistors that we estimated to get the results that we wanted. And this is the result that we get from this circuit, 10-volt gain, because the difference between the inputs was 1. And then we tested the common mode rejection, which is essentially putting the same input in both op-amps of the instrumental operation amplifier, and we should get 0, ideally, and this is what we get on the simulation. So after that, we did the implementation, and Homero is going to be explaining the implementation part.
So here it is. Here is the implementation. This is the physical circuit that we designed. And right here, it's currently set up to do the common mode gain circuit. So we can see right here that it is 2 inputs in the same place and to the 2 different op-amps, VN right here, VN1 and VN2. So here we decided to change the resistor values to simplify it. So we eventually got R1 of 1K, R2 of 10K, R3 of 1K, and R4 of 10K. So for the first step, we decided to do the measure the differential gain. So to do that, this is the function generator we used, and we applied a 0.1 volt peak to VN1, and VN2 was grounded. So to get this is our results for the oscilloscope, where here is the RMS value of 35.44 millivolts and an RMS of 360.08 millivolts for their output. So that would give us a gain of approximately 10. I'll show the exact value in a moment. Here was the common mode function generator we used. So we applied 5 volts peak to peak to both the VN and VN1 and VN2. And this was to do the oscilloscope. I had to enable only the input and the output separately to better view it. So here we got an RMS value of 1.767 volts input, and the output was 15.09 millivolts. So here is our data table, where the differential gain circuit has this as the input voltage for VN1, 0 volts for VN2, and this is our output for Vout. This was expected to get a gain of 10, and we got an actual gain of 10.16. And as for our common mode gain circuit, the VN1 and the VN2 had the same voltages, so 1.76 volts RMS, I want to specify, and a voltage out of 15.09 millivolts. Our expected gain was 0, and our actual gain was 0.0854. So to find the common mode rejection ratio, we have to use the 20 log of the differential gain over the common mode gain. So this was the equation we used and filled out, and we got an actual common mode rejection ratio of 61.508 dBs. which was very good since the expected value for an LM741, 3 LM741s is between 50 and 70 dBs. So we got an expected value in that range. Here we have the Bode plot showing the frequency response logarithmically of the differential gain circuit, which has a gain of around 20 dBs. Exactly, it says here 19.9. And then this is the linear circuit, linear Bode plot, showing that the gain was in the expected 10 region with the 9.88 gain in the Bode plot. Here is the common mode gain circuit, where we had a negative gain in dBs of negative 38.81. This was a logarithmic Bode plot. And here is our linear Bode plot showing that it is around the zero value, which the ideal zero value. In actuality, it was 0.01 as shown right here. So we were able to get really close in all our actual values, nearly getting to our expected values. So I think we did a really good job here in this part. And that is all.
That is all. Thank you guys and stay safe.